All right, so today we're going to spend a little bit more time with this integral that we were pretty focused on yesterday. So let me write it again. So we'll start by sort of finishing up our study of this simplest heavy-light integral. And I don't care about the factors for now. I just want the simplified form right here. So this went like log mu squared over big M squared plus 1 plus M squared over big M squared log M squared over, oh, I'm looking at the wrong one. I want the T-channel one, which is here. Doesn't have the 1. Good. Okay. That's all we need. So what we're going to start today by revisiting this integral. In particular, right, we were focused on this log lambda term here. And so the big punchline of yesterday was I taught you how to use effective field theory techniques to separate scales in the sense that you could match at one loop, which would eliminate all of the log little m dependence at the high scale so that your high scale matching was analytic in little m. Then we ran down to the low scale and we computed one loop corrections at the low scale that reintroduced logs of little m, right? And then we understood the sense in which matching plus RGE running plus one loop corrections is reproduced the full integral, when we included all the diagrams. But in particular, right, we were really focused on this log because this is the thing that up until yesterday you may not have ever seen how to resum, okay? And there was this subtlety that the resummation had to be consistent in power counting, so it really wasn't a resummation. But today we're going to build up to a theory, soft collinear effective theory, at least a scalar version, which is going to have logs at leading power that are only dependent on a ratio of physical parameters. And so we're going to use exactly the same techniques to resum those logs. So that's really the main place where we're going, and that'll kind of close us out next time. But before we do that, I want to teach you a very weird procedure called the method of regions, which lets us analyze this integral as a perturbation in the power counting. And the reason we're going to do that is because while this was a case where we could actually do the integral, the Sudakov integral, which we'll get to by the end of lecture today, is a case where you can't do it, as far as I know, to all orders in power, but you can do it as a power expansion. You can actually do the analytic integral. And the cleanest way to do that, or one way to do it at least, is to use the method of regions that I'll show you now, okay? So where we're going is we're going to use the method of regions to understand this case that I think is probably pretty clear what to do as far as just computing in a straightforward way following, say, Peskin. And then we'll apply that same technique actually next time, where we'll use the method of regions to compute the Sudakov integral. Okay? So in order to understand the method of regions, maybe I'll do this here. We need this aside that scaleless integrals vanish in dimreg. And this is going to be really important for understanding how the method of regions works, because what the method of regions is going to do is we're going to essentially do something kind of like a Taylor expansion, where we're looking for taking the full theory integral and breaking it into pieces that depend ideally on a single scale, and then everything else in the expansion will be scaleless and will be automatically 0. Okay? So I'm going to show you just an example of this, and then I'll tell you that it's a general phenomenon, and if you're interested, I could point you to some more elaborate discussions. But so let's just look at an example. So let's take the log divergent integral, with no scales, okay? And again, here, this notation, right, this is d to the dl over 2 pi to the d, okay? So this is log divergent, and if you want to evaluate it using, say, the appendix in Peskin, it's convenient to break this into 2 pieces. So you can introduce a mass as follows. This should be L to the 4th. Okay, so take just a moment to convince yourself that if you add these two together, then you get back to the scaleless integral, right? Do you see it? Just multiply this by L squared over L squared, right? And combine them, and then this will cancel the numerator, right? Clear? Yeah? Okay. So now these are just two integrals that we can use Feynman parameters and go through the exercise of doing. This one, you know, if you just are following your nose, you need the 3 Feynman parameter version, whereas here you can just use the 2 Feynman parameter version. I'm not going to do the details of this, but I'll tell you the answer, and you should. I encourage you to go and check it offline. But one thing to notice about this division is what we've done here is we've divided it into 2 integrals. One, which is, let's see, this one is UV divergent, right? But not IR divergent, because we have 4 L's in the numerator, but this M is going to regulate the IR for us, right? Whereas this one is UV convergent, because we've got 6 L's in the denominator, but it's IR divergent, right? As we go to the IR, this L to the 4th is going to give us a divergence, okay? So we have I UV, I'm going to call it, and I IR. So again, it's totally straightforward to evaluate the integrals, and what you'll find is that IUV is I over 16 pi squared times 1 over epsilon, I'm going to call this epsilon UV now. Oh, and let me be a little pedantic here. So now I want to say I have 2 mu's. I have a UV mu and an IR mu. Of course, those both came from the same source, so at the end we're going to set them equal, but the point of this exercise is to separate these 2 contributions. So I have 1 over epsilon UV. Yeah, that's exactly what I just said, right? Yeah, so I'm separating these 2 things. I'm going to treat them separately, and at the end I'm going to set it equal so that it all works. Okay. Yeah. So, no, that's good. So we have log mu UV squared over little m squared plus 1 plus higher order and epsilon terms. IR is I over 16 pi squared 1 over epsilon IR plus log mu IR squared over m squared plus 1 plus higher order and epsilon. Okay? So then you add these together. And if you set the mu's equal, then what you get is I over 16 pi squared 1 over epsilon UV minus 1 over epsilon IR. Okay? So what we've done is we took this scaleless integral, we divided it into a UV divergent and an IR divergent piece, okay? We regulated with dimreg, and then we see that if we recombine them, and if we set epsilon UV equal to epsilon IR, which of course it has to be the same regulator if it's one integral, right? Then we get 0. Okay? So this is what we mean when we say scaleless integrals vanish in dimensional regularization. This is an example, but it's a general phenomena. And not only does it happen in general for integrals like the ones we're familiar with, but it also happens for integrals with linear in L denominators, which we're going to see show up in the SET example. Okay? And actually there I'm going to show you a new kind of Feynman parameter trick to be able to evaluate those integrals, which is pretty cool. Okay? So one of the points I want to make here is that scaleless integrals vanish. Another point I want to make is that if I just wanted to evaluate that integral, and in particular if I were interested in isolating the UV divergences of that integral, then I can do that in dimensional regularization. I could just, for example, add a mass parameter into the denominator there, right? And that mass is going to regulate the IR for me, right? So it's going to give me an explicit mass regulator in the IR, and dimreg is going to regulate the UV, okay? This is again what we're going to do in the SET example, okay? Is that where we're headed is in SET, I'm going to show you a really simple way of thinking about the fact that by matching onto the effective theory, we're mapping the IR divergences that we're interested in resumming into UV divergences. And then in the effective theory, we're going to take integrals like this one, or the analog of this, we're going to regulate the IR with a mass, okay? So that makes all of the IR divergences very obvious. They're going to show up as logs of that mass regulator. And then we're going to get 1 over epsilons from the UV alone, and that's going to give us the anomalous dimensions that we can use to resum logs. Okay? So again, by the end of lecture, a lot of those words will be dressed up by expressions, but this is this very important technical point, okay, to keep in mind. And in particular, this is why we can use this method of regions that I'm going to show you next. Okay? Because if we can expand all of the mass dependence away, then everything else we're left with is scaleless, and so it vanishes. Okay? Any questions here?
I'm curious if you have another way of thinking about this. I mean, is there a sort of conceptual or intuitive way of thinking about it, or do you just kind of make reference to this calculation?
No, good. Actually, yeah. So there is a very intuitive way of thinking about it, which is that dimreg is going to give you logs of mu, right? From the mu to the 2 epsilon, right? But then inside that log, if it's going to be sensible at all, you need another scale. So if you don't have any other scales around, there's no way to have a consistent picture where you have a log, and the log is really associated with the non-zero divergence, right? So it's really the fact, that's why it's the scaleless property, right, is so critical, because there's nothing else to put inside the log to cancel the mass dependent, the fact that mu carries mass dimension. Yeah, thanks, that's a great question. Yeah?
So you say scaleless, what precisely is the scale that you're currently absent? Like, is it lambda, or is it that there's...
No, it's m, right? So this integral on the left has no little m's in it. It has nothing besides the loop momentum that carries mass dimension. Okay, so that's what I mean. There's no dimensionful scale inside the integral. Okay? Yeah, very good. Any more? All right. So let's come back here and talk about how to do this with the method of regions. So the method of regions is this kind of funny way of Taylor expanding. It's not a Taylor expansion because, I guess, yeah, so let's take this integral. So it's not a Taylor expansion because we're going to take the integral and we're going to expand it many different times to give us different terms, right? With a Taylor expansion, you just take the function, you expand it once, and that's the expansion. So it's kind of in the spirit of a Taylor expansion. Oh, sorry, I'm writing from the wrong spot. Shoot. Yep, that's this integral, right? Our heavy light integral. And, oh good, I'm just going to do it in 4 dimensions for this example, okay? Well, I had 4 there already. Good. All right, so this is the integral we're gonna study. And what do? Well, we look for scalings of our momentum in terms of our power counting parameter that give us a total scaling of this integral at whatever order in the power counting expansion we're interested in. Okay? So here's where the power counting really starts to get extremely powerful, is that we can look at this integral, and schematically we have 4 powers of L in the numerator, and then we have these various denominator factors, okay? So let's take, for example, what we'll call a hard scaling for the momentum, which is that the loop momentum is order 1 in terms of our heavy scale. And again, underlying all of this, you should have in mind the process we're considering, right? It's our old friend phi-phi scattering at threshold. And so we know that doesn't break Lorentz invariance, so we better not look at any scalings that are non-Lorentz invariant in this simple case, okay? In SCET, we're going to break Lorentz invariance. We're going to have a hard light-like direction. And so then we're going to look at non-Lorentz invariant scalings, okay? But here we have Lorentz invariance, so let's just take this to be the scaling of our hard loop momentum and see what happens. So if I take my integral I can look at the numerator. This is just going to give me order 1, okay? Everything in units of big M. Now let's look at the denominator. So I want to Taylor expand each piece. So I have L squared hard minus M squared. What's the leading contribution in terms of power? So if this is order 1, this is order lambda, right? So it's just L hard squared, right? So this is L hard squared plus order lambda. Okay? Let's do the other denominator. What do I do with that?
That's just M squared. Big M squared.
But L hard is also,
It's 2 times.
yeah, so both factors, sorry, yeah, I think I heard it over there. I need to keep both, right? They're both of the same order in this power counting, right? This is order 1 and this is order 1, okay? So this denominator just is L hard squared minus big M squared, okay? Now,
Sorry, I got a little split the integral into a hard part. So far you're trying to do the integral into
that's correct, yeah. Yeah, so it's, again, it's a little bit weird procedure, but you'll see in a moment that it's going to reproduce order by order the expansion of this full integral, okay? So that's what we're trying to do. We're trying to come up with a scheme that can systematically expand, do the integral as an expansion in lambda, okay? So I assume a scaling. I Taylor expand my denominator, okay? And then I look at the scaling of the numerator divided by the scaling of the denominator. So let's actually say, write down this integral now. We have d4L over L squared times L squared minus big M squared. Okay? The numerator scales like order 1. This scales like order 1. This scales like order 1. So this is going to give me an order 1 contribution to my integral. Okay? Notice it's log divergent in the UV. It's finite in the IR. So any guess for which term it's going to give me? In my full theory, in my expansion here? The first one, right? Because it depends on big M. This is an avatar of the UV divergence, right? This log. And so sure enough, this is an integral we've now done a few times, right? And it's going to give me exactly that log back, plus some factors that will end up working out. But here we're working to subleading power, right? We've gone to order lambda in the expansion here. So I want to make sure that I capture not only the order 1 pieces when I do this expansion in regions, but I want the subleading power pieces as well, okay? The order lambda squared piece. So let's make sure we get the order lambda squared piece. Any guesses for what that looks like? I have this denominator, and I want to expand it around with this scaling for the loop momentum and get something that's order lambda squared. Which one? The first one. Yeah, so the first denominator has the little m in it, right? So if I expand this to next order in the Taylor series, then I'm going to get a subleading power contribution of the integral. So that looks like this. Right? So that's subleading in power. It's order lambda squared. Let's do another scaling. I'll evaluate them for you in a moment. So we're going to have a soft contribution. How should it scale? We need an m in front just to keep track of the units. And then we can use any power of lambda we like. We could use order 1. We can use order lambda squared. So anyone want to take a shot? Let's do something order lambda. And again, we're going to make all the components scale equally because we want to keep Lorentz invariance. Okay? And then now we want to play the same game, right? So let's look at the denominators. L soft squared minus m squared. How does that scale? How does that expand? What do I do? We could both, right? What about the other one? Yep. We just get minus big M squared. Okay? So that gives us the soft integral. How does that scale? How does that integral scale now? I got 4 powers of L. That goes like in total lambda squared, because this goes like lambda to the 4th. This is lambda squared. This is order 1, right? So this thing is ordered lambda squared. Now my claim is if you assume any other scalings in terms of lambda, you're either going to get a scaleless integral, which vanishes, or something that's higher power in lambda, which we're dropping, right? Because we're expanding in lambda. Okay, so that is something to think about quietly on your own. It's really pretty easy. You just try lambda to some power, right? You could probably do it in your head quickly. You could try a few, and you'll see that it's either higher power or you're just going to get something scaleless. Okay? Yeah?
Is lambda m, little m over big M or little m over big M squared?
It's little m over big M.
Okay.
Right? Yeah, this is lambda squared. This is lambda squared, right? Yeah. So what we've done is we went from a 2-scale integral down to a series of single-scale integrals. Okay? So notice, right, these guys all depend on big M because they're at the hard scale. This one, you can pull the big M squared out in front. That, you could imagine, comes from tree-level matching, the way it did yesterday. And the denominator then, the loop integration, is only going to depend on little m. Okay? So this is the sort of mathematical procedure. If you want to just blindly take an integral and understand it as a power expansion, you can do this regions analysis, and you'll get order by order a Taylor expansion in lambda of the integral. And again, all you need is to decide what order in lambda you want to go to, and you want to decide, and you need to use the fact that scaleless integrals vanish. Okay? And single scale integrals are essentially all analytically tractable, certainly at one loop. And so you can take, for example, the Sudakov integral, which is pretty nasty, has a couple of scales in it, and expand it in regions, and do the integrals, the single scale integrals individually, which is what we'll do tomorrow.
You can keep expanding the I sub h by I sub s. Can you
Yeah, because this denominator gives you higher power. Yeah. Right?
What happens if you have a third mass scale, somewhere between the two, that's not like, so like if you had intermediate mass scale, you can neglect.
Yeah, then you just have to keep matching. It just gets nastier. But yeah. We're going to stick with our 2-scale problems. They're already bad enough. Okay, so now we can evaluate these integrals. We're going to do it in dimreg. I think at this point we've done both of them. I'll just tell you the answer. So I hard 0, mu to the 2 epsilon, integral dl, 1 over L squared minus big M squared, L squared, that's I over 16 pi squared, 1 over epsilon plus log mu over big M squared plus 1. So as promised, our UV log is there. And now that we see the expansion in regions, this is the only place the UV log could have come from because everything else is power suppressed, right? Next, let's look at the leading power soft. So, or sorry, I'll do the hard next. So the subleading power hard integral, I don't know if I should change notation, right? Based on what you guys said yesterday, this should be 2 technically, but I used 1s yesterday because it's the first contribution at subleading power. So just take this integral from the hard expansion and we get I over 16 pi squared, little m squared over big M squared, 1 over epsilon plus log mu squared over big M squared plus 1. Okay, notice if, first of all, that this is the integral we did here. Where is it? Oh, I erased it. Haha. But it was, well, they give you the same answer, but I think it was the IR integral, right? Because it's IR divergent. Yes, thanks. Notice also, there's a 1 over epsilon here, right? But there's no 1 over epsilon over here that's at subleading power, right? The subleading power terms are finite. So one really critical sanity check, this is a trivial example, right? But in the Sudakov case, we're going to see a lot of spurious 1 over epsilons appear between the different regions, and they're all going to have to cancel to give us only the 1 over epsilon poles from the full integral, okay? So this is a really critical sanity check, right? We know that we can't have any subleading 1 over epsilons just by studying the integral, right? It's pretty obvious. And so, so this is going to have to cancel, and obviously, right, it's going to cancel against something from the soft integral. So let me write the soft integral for you. At subleading power, so mu to the 2 epsilon integral dl. This one is 1 over minus m squared, L squared minus little m squared. That's our quadratically divergent integral, minus I over 16 pi squared, little m squared over big M squared, 1 over epsilon plus log mu squared over little m squared plus 1. Okay? And lo and behold, we reproduced our integral to subleading power, right? You add those together, you see
There's still a 1 over epsilon without the m squared over m squared from the
yeah, so sorry, I should have left it there. I mean, I regulated that already, right? Yeah, so did I write down the wrong? Yeah, so let's see. I probably wrote this down wrong because it definitely gives you the right answer. Does anybody have yesterday's notes in front of them? You have the +1. Yeah, okay. So there should be a +1 here. Sorry. Anyway, it's better if I don't get all the factors of 2 right. It gives you something to do at home. Right? We get our, and let me add the 1 over epsilon also, because I shouldn't have dropped it, since we're just looking at the unregulated integral, or the, sorry, I didn't add the counter term, right? So there's really a 1 over epsilon here. So we get the 1 over epsilon, right, from the UV divergence. And then at subleading power, right, this minus sign was key, came from the Taylor expansion. And it cancels these 1 over epsilons. It cancels the 1s. The mu's then cancel between these two. And we're left with our the log that we were obsessed with yesterday, right? So this is a method of regions. Yeah?
So I think because the power content, LS is order lambda times capital M. But when you do integral, you are integral 0 to infinite.
Yes.
So well, that means that also for the other power content, you also have 0 to infinite.
Yes.
Is there a double continuous thing?
Yeah, that's a part of what makes this so non-trivial. Okay, so this is it's a bit mysterious. You can kind of think of it in terms of what we're really doing in this regions analysis is at some level we're expanding around some pole, kind of. Okay, and again, at the heart of this whole thing is that the scaleless integrals vanish. So the fact that we're integrating over all of this momentum space, most of which is far away from where the singularities are, means that it just vanishes because the scaleless parts vanish. Okay, so again, I definitely encourage you to just spend a little quiet time thinking about the various ways you can expand this integral, right? Because you can, in principle, make all kinds of choices for the scalings. Oh, the soft is here, right? And you're either going to get something subleading power or scaleless. Okay. Now, so yeah, that actually brings up another excellent point, which is we can notice now that L hard squared is order 1, while L soft squared is order lambda squared, right? So these modes are separated in terms of their invariant mass scale, okay? So the really non-trivial thing about this is just some trick for being able to calculate the Taylor expanded integral. But then the deep insight is each of these regions is going to correspond to a mode in the effective theory. And we saw that, right? We had the hard scale matching, right? So there's always going to show up a hard scale that's going to contain the matching contributions. And then in our example from the last few days, right, we had this soft mode. And so that corresponds to this soft scaling, right? And it has mass of order little m squared, of order lambda squared. So again, and by the end of lecture, I'll tell you about the modes for SCET. In SCET, we're going to have a longer list of modes that we have to keep. And we can check whether or not they are going to be overlapping or not based on whether they're separated in terms of their invariant mass. Okay? So I'll show you that. That's going to come up by the end of lecture. But here, this kind of gets at your question. We don't have to worry about the double counting because these really are separated by our power counting. Okay? There are issues of double counting that come up in SCET when you have modes that all scale the same in invariant mass, and then you have to be very careful with the way you do the integrals. Okay? So again, I'm being fast and loose. I mean, there are always subtleties with these things, but roughly speaking, you can say because of this fact, we can just naively integrate each of these and not worry about any overlap problems. Okay? Yes? So, So there's one paper that I'm aware of that I have not studied in detail because it's a mess. I mean, the aspect of this procedure that is very weird is that we're taking the same integral and we're doubling, or we're multiplying that integral into every region that we're keeping, right? It's not a real Taylor expansion. We didn't take the one object and Taylor expand at one time, right? And so, yeah, so I'm going to give you a physics answer, which is that it works. And if you're curious, I could point you to this paper. Yeah, and you know, perhaps the original paper, which I should have written the reference down. It's by Beneke and I forget now. Is another thing worth looking at. I'll write it into the notes when I post them.
So kind of in the same vein, and maybe this just isn't worth belaboring, but isn't there like a transition region where neither expansion is good?
Yeah, then you wouldn't do an effective field theory analysis. So if lambda is not a small parameter, then you may be in this place where your logs are pretty large, but not so large that you would resum them, or yeah. So, but here we're assuming we're in this simple case where our scales are widely separated, and so we have a really, really nice expansion. Yeah. And one thing that comes up in this business is there are, so you have fixed order results when the scales are not so separated. Those are a good approximation there. You have the resummed results in a region where the scales are widely separated, right? Maybe an extreme of phase space. And these things are smoothly connected in principle. And so there will be this intermediate region that you're talking about, and there are a variety of techniques. They call it profiling. So there are ways that people essentially extrapolate between the two. And you know, it's not as bad as just drawing a line between them. There's a physics motivation. Essentially, you change, one of the ways that they do this is that they change the scale setting in a non-trivial way. But yeah, it's subtle. And so, yeah, so we're going to avoid all of that complication.
Scales where L is large enough that it can't be disregarded, just discarded with respect to big M. L is also large enough that little m is negligible in comparison.
Big M.
If
I mean, this captures the UV divergence, right?
yeah, that's
So
what,
there's.
well, I'm saying with respect to that intermediate region, if you're in a regime where little m is not negligible compared to L, then you are in a regime where L has to be negligible compared to M, big M.
That's not, I don't think that's really what we're doing here. So it's really a question of L, then we integrate over all values. So in each of the integrals here, right, that's an integral from minus infinity to infinity in all four directions. Okay, so there's not a sense in which we're keeping L in some range or anything like that, right? We're just using this to Taylor expand each of these integrals to keep the leading pieces or the subleading pieces, and then we integrate them using Dimreg. So yeah, it is really more akin to contour integration. But I can't give you a precise mapping. Okay, these are great questions. Any more confusions here? Otherwise, I'll move into. They let me Taylor expand the denominator differently, right? That was my full integral. These are different. Each of these is different than that one.
But in both cases, you're actually the range over which you're integrating L includes both L's.
Yeah, that's exactly. And that again is related to the scaleless integrals vanishing. Yeah. Okay. So let's start talking about a scalar version of SCT that's soft, collinear, EFT. This is a really fascinating theoretical structure, and it's ubiquitous throughout gauge theory because gauge theory is characterized by these soft and collinear divergences. Okay, and so I guess Frank talked to you quite a bit about these. Maybe Kieran also. So you're at least familiar with the idea, but we're going to kind of approach it from this other point of view using effective theory techniques. Okay, And so in order to do this, before I even get into why or the physics or anything, I want to start by just setting up some notation, because we're going to work in light cone coordinates. They may be unfamiliar to you. They're not so hard, and we're going to, but it's it's just how the theory is defined. So we start with a collinear direction, which is just a light-like direction. We'll call it n, and we'll point it in the z hat direction. Okay? So clearly, n squared is 0, right? It's light-like. And this is going to be the background we're going to expand the theory around. So the idea is we have some process, and it makes a very relativistic, massless particle. Okay? And then we want to expand the soft and collinear divergent structure around that hard line in the background. Okay? So the theory is going to be set with this light cone choice, right? And then we're going to do an expansion around this light cone. Then we want to define an anti-collinear direction. It's usually called n bar mu. And we need it also to be light-like, and for it to be in the anti-collinear direction, opposite the collinear direction, we're going to enforce that n dot n bar equals 2. Okay? And that might seem a little weird, but let me give you the canonical example of the anti-collinear direction. I'm just pointing the light cone in the minus z direction now. And take a moment to convince yourself that that dot product gives you a 2. Okay? Now, for everything we're going to do, you should just keep this explicit version in mind. But notice that you can, in principle, rotate this as long as you keep it light-like and enforce this. There's a whole family of choices you can make here, right? So then we want to decompose a momentum vector, or any vector in the theory, in terms of these vectors. So we have n dot p over 2 m bar mu plus n bar dot p over 2 n mu plus p perp, which is a 2 vector. And so here, right, you can see this is self-consistent. If I take n dot p, right, p perp, by the way, is defined, perp is defined orthogonal to n and n bar, right? It's the perpendicular direction to the light cones. So clearly, if I dot in with n, the perp contribution is 0. It's orthogonal. Okay? N dot n bar is 2, so that gives me n dot p back. And n dot n is 0, so that kills this term. Okay? So it's just a self-consistent way of expanding the momentum, writing it in terms of these variables. And it's not going to come up for us because we're not going to, but just because it can be confusing if you're looking at the literature or at the review articles, there are minus signs just to keep track of. So again, in this canonical frame, the perp would be in the 1 and the 2 directions if this is 0 through 3. And so then with this definition of what we mean by p perp squared, it has the minus signs from the Minkowski metric already built in. And so then we would get p squared is n dot p m bar dot p plus p perp squared. Okay? So unfortunately, there's just some convention dependent thing here. Some people do it with a minus sign here. Some people do it with a plus sign. Okay? So it's just a minus sign to make note of. Another thing that I personally find confusing, I have to think through carefully every time it comes up, is that if you look at this, n dot p points in the n bar direction. So that's just life, all right? And if you look at Ian Stewart's notes, I decided not to introduce extra notation, but I think, so he would call, actually, I think this one he would call p plus and this one p minus, but I could have them backwards because I confuse it all the time. I think, frankly, he does that because then you don't have to look at n dot p and say it points in the n bar direction, right? Yeah, I decided not to do that for better or worse. Okay, so now here's the notation that's going to be really powerful for us. we're going to write p mu as something that looks like a 3 vector. Sorry. Okay, so from here forward, I'm going to start writing momenta with only 3 components. That's because we've broken Lorentz invariance in this very particular way, right? We have a background light cone that we're expanding the theory around. And so there's the light cone direction, the anti-light cone direction, and the 2 directions perpendicular to that. So just like when we did the method of regions over here, where we expanded homogeneously in all directions, now we're allowed to, in principle, expand in each of these directions separately, but perp, we have to expand these together, okay? Right? Because there's some perpendicular space that's that has, full rotational invariance, okay? So, I doubt I'm going to have time, but if I do, we'll come back to reparametrization invariance. Jeez. So this is known as RPI. And let me just tell you very briefly, what it does is it encodes the residual Lorentz invariance that we have when we took a Lorentz invariant theory and expanded it on a light cone, right? So there's 5 generators left unbroken. Those are the 5 generators of RPI. They correspond to these directions that you can choose when choosing n versus n bar, okay? And then there's an overall rescaling of n versus n bar such that n dot n bar equals 2. So this encodes all of the ways that you can move things around to satisfy those 3 constraints up there, okay? Again, if I have 5 minutes or so at the end, or if you guys want to chat during coffee, I can write some formulas for you. This is also in all the reviews, and then can't help but plug a paper that I wrote looking at soft collinear effective theory and supersymmetric theories. There we worked this out for 2-component fermions because we were looking at SUSY theories, and I think it's pretty clean in terms of 2 components. So if you're interested, that's a place to look. You could go check out our RPI section. I think it's pretty clear there. It's also nice in Ian Stewart's notes and in the Becker review and so on. Okay. So let's talk about physics a little bit. Now we have this notation, we have this framework, we can talk about a collinear direction. Why do we care? We care because of the IR structure of QCD, or gauge theory generally. So, our goal is to model the IR divergence structure of gauge theory. I'll just say QCD. Right, but gauge theory generally, and really field theory generally, because I'm not going to probably show you any gauge theory. We're just going to do everything with scalars. So, what's one way of probing the IR divergence structure of gauge theory? You can just look at a tree level diagram, and you can look at an extra emission, and then study the scalings with momentum as you take that extra emission, say collinear or soft, with respect to the hard line. Okay? So here's our model. So I'm going to use a phi cubed theory. This is some dimensionful coupling constant. And then I'm going to introduce an external source, we'll call it J, that generates phi squared for me with some momentum. Okay? So I'm being a little quick here. J, you can think of J as having some scale associated with it. Okay? So an insertion of J, which I'll draw as a blob, just generates 2 phis for me with whatever that hard momentum is. Okay? So that sets the hard scale of the problem. Right? You can imagine that J is coming really from one of the canonical calculations that people do is this jet measurement, a jet variable called thrust. And one of the first calculations was E plus E minus to QQ bar, say, really and here, right, you can just call this whole thing J. So we have something inputting energy that's generating our final state of interest, right? And we don't really care what it is as long as it factorizes off from our final state, okay? So if you like, this could be my heavy scalar decaying into a pair of light scalars, right? That's a great model for this. I just wanted to keep it agnostic and also to get you a little bit comfortable with this idea that you can isolate the part of the diagram that you care about, right? The final state, which is going to have the IR collinear and soft divergent structure, and just study that by itself, okay? And connect that to any hard process you want. As long as with QQ bar here, it's a little more complicated because now they can in principle talk to each other at next leading order, right? So that's what J means. So let's take J, let's make a pair of hard scalars, and let's use our cubic here to just split off P1 and P2. Let's take phi massless for now. So this is some amplitude, and then I'm just going to study this part of it. Okay, so this thing goes like my coupling and 1 over 2 P1 dot P2. So now, let's point P1 in the n direction. That's going to be our hard line that we're going to do our expansion around. And let's say P2 is exactly collinear to it, so it also points in the n direction. Then P1 dot P2 is 0, and we have an IR divergence. Right? It's just coming from this propagator. So it's really this intermediate state, right, that's giving us the divergence. And if you go read Peskin, he'll talk about resolution effects and so on. There's a physical interpretation of this. You can cut it off by saying that you can only measure the fact that these are distinct from each other to some finite resolution and so on. There's a nice physical picture there. That'll at some level play, you can kind of keep that in the back of your head, but we're going to keep it simple. And we're going to regulate this by letting P2 be collinear but not exactly collinear to P1, okay? And that degree of collinearity is going to define our power counting. All right? So we're trying to isolate this collinear divergence. I'll talk about the soft in just a second, but we're trying to isolate the collinear divergence by going almost collinear, right? And then we're going to do a Taylor expansion in how collinear we are. Okay? So I'm going to show you how to do that concretely by the end of today. Let's look at soft. So soft means P1 goes to 0. Sorry. P1 is still n. I wrote this wrong here. P2 goes to 0, right? And sure enough, P1 dot P2 goes to 0, right? So again, this is saying I have my hard line, and then I emit a particle that is so soft that I could never see it. And we associate that with an IR divergence because you could do that an infinite number of times, right? And you would never distinguish the fact that you had a hard line or a hard line plus an infinite number of soft particles, right? It's the same thing with the collinear. That's another way of saying it, right? Is I could have an infinite number of collinear splittings that are very, very tight together, right? And I couldn't distinguish that from just having my original hard line, right? Okay, so let's regulate these divergences by picking some scheme, some nice Taylor expansion away from, or that approaches the collinear limit in a sensible way. Okay, the soft limit's easy. The collinear limit's a little bit subtle. So we want to regulate these. So again, we're going to point P1 equals magnitude P1 in the n direction. Okay, that defines our light cone, right? Picks the frame. Breaks Lorentz invariance up to RPI. And now we want to talk about P2. So this is collinear. To be n mu plus fluctuations. So let's model the fluctuations. And let's say, just to because we have to define a power counting parameter, let's take the perp direction, right? However little bit of momentum we have in the perp direction to define our lambda. Okay. So let's say that we have a fluctuation in the perp direction of order lambda. So give P2 a lambda component in the perp direction. That tells us P perp squared goes like lambda squared. Okay? So now, if we look at, so I think I have it over here, although I probably could have written it as fast as I walked. Right? We have this for P squared. So now we're saying P perp goes like lambda squared. We've pointed our particle in the n direction. That means m bar dot p goes like 1. Okay? So if we want both components of p squared to contribute, this sets the scaling for n dot p for us. So what does it need to be? Lambda squared. Okay? So this is how we power count collinear momentum. We say collinear momentum goes like lambda squared 1 lambda. Okay? So you've probably, I don't know how many of you have seen this before, but it's kind of mysterious. But actually it's just this simple case. Said another way, you want to be able to take this thing on shell, right? So it better be able to, the only way for it to go on shell if the perp components are order lambda squared, the perp component squared, is to have a contribution from this direction. You can also convince yourself that if you added order lambda contributions to the 1, they would always be subleading. Okay? So again, as a homework assignment, I recommend playing with this form and convincing yourself that these simple requirements, they're very physical, force you to take a form like this. Given that this is lambda, this has to be 1 in lambda squared. Okay? There's an even more physical way of seeing this. So if you didn't believe those kind of tilde arguments, then another thing you can do is you could take a particle in its rest frame in light cone coordinates. You could boost in the minus z hat direction. And I'll just tell you what boosts look like in light cone coordinates. If I have some parameter kappa, which I'm going to define as 1 over my power counting, so that's the boost parameter, then this shifts n bar dot p to kappa n bar dot p, and it shifts n dot p to n dot p divided by kappa, which gives me exactly the same scalings. Right? So that's two different ways of seeing this kind of weird form. But this is really modeling a lambda squared distance away from the light cone. Okay? And then, now we have a power counting scheme, right, for the collinear momentum. So what are we going to do? We're going to pick a process with a collinear divergence, and we're going to perform the method of regions using this power counting, and we're going to find a non-trivial contribution from this region, right? So that's where we're going. We'll do that next time. There are also these, and yeah, any questions? Because this form is critical. Please. good. Yeah. So this is the. Think of this as the as being multiplied by n bar mu. Yeah. Right. So this is the coefficient of n bar mu. So I was a little sloppy here. Yeah, it wasn't a stupid question. Right. So it's really this, because this is just, these are just picking perp and n bar are just picking some way of expanding the momentum. So it's this thing that's going to need to change under a boost. Right. Yeah. Does that make sense? Okay. So,
is the n bar, the p is over the 1 because of the thing you said, that's the component that actually points in the n direction.
correct.
I see.
Yeah, exactly. So when I write, where do I have one of these? When I write this, right, and I use, now I want to say this goes like lambda squared 1 lambda, right? So n bar dot p is the suppressed one. That's in the, n dot p is the suppressed one. That points in the n bar direction. Okay? So this choice, again, right, it's confusing. This choice points in the n direction. So this is a collinear particle, right, pointing in the n direction. Yeah. Any thoughts about what we should do for soft? How should we power count a soft momentum?
Power counting of the collinear.
Yeah. Right, so you guys are both right. And there's one, what's the key reason that I'm looking for? So what does soft means? That we have just soft particles in any direction, right? It's isotropic. So I need to power count equally in each component because of Lorentz invariance. I think it's maybe too obvious. I don't know if that was too leading. Right? So Lorentz invariance, right? I have a soft particle. It can go in any direction. Again, if you think about your hard line, you can emit a soft particle any direction. You're still going to get a divergence, right? Whereas the collinear divergence, you had to be collinear to the direction. That's why it has this directionality built into the power counting. Okay? The soft particle is just isotropic. So it turns out in SCET, there are actually two versions. No, it's going to be the same lambda. Yeah, so, and actually, maybe this, good. So, I think it'll be clear by the end of today that it has to be the same lambda, but one of two versions, okay? So we have what's called P soft. That's going to go like lambda, lambda, lambda. And we have also what's called P ultra soft, which goes like lambda squared, lambda squared, lambda squared. So here's where picking a process comes in, okay? You might say, the examples I've shown you, I kept emphasizing this pick a process part, right? And it seemed really artificial because it kind of was. But depending on the process you choose, you end up with soft modes contributing or ultra soft modes contributing, okay? So the type of SCET theory you want to use, this one is called SCET2. This one is called SCET1. And so depending on your process, you get SCET2 or SCET1. We're going to work with the massless Sudakov integral. That's going to be within SCET1. And then we see P squared ultra soft goes like lambda to the fourth, whereas P squared soft goes like lambda squared. Yeah, so in the example I show you, you'll see there's no lambda squared. There's no soft contribution to the integral. Yeah.
Sorry. Is lambda the perpendicular displacement from the n direction or from P1, between P1 and P2? So P sub c, is that the momentum of particle, is that P2 or is that P1?
Oh, I see what you're asking. Yeah, that you should think of that as P2. So think of P1 as defining n,
Okay.
and then we're expanding fluctuations of emissions around P1. Yeah, around the first particle. Yeah. Good. So then depending on which of these scalings I have, right, I don't think I need to write anything, but I get either a 1 over lambda squared or a 1 over lambda to the, I get a 1 over lambda or a 1 over lambda squared type divergence, right, and when I regulate this, this tree level emission. Let me draw a picture that I think really illustrates a subtlety that makes this stuff a little more challenging. Also, so then when you go read Ian's notes, you understand how to interpret this. Which is, I'm sure after this lecture, you're all going to stay in from the hike and go check out Ian's notes. Yeah. That's right. Yeah, exactly. Yeah, so this is giving us a parameter to approach the IR divergence with, right? Just like you would with a mass. Yeah. But a mass regulator would always be Lorentz invariant. So let's take the hard scale to be 1. I've already kind of done that over here. So SCET1, which is the one we'll do calculations with next time, looks like this. So this is the mode structure. So this is n dot p direction. This is the n bar dot p direction. Somewhere up here is the hard scale. And then we have, so let's see. This should be a 1 and a 1, right? Because the hard scale is order 1 in all the directions. And it follows the p squared equals 1 cuts out a parabola in this parameter space, right? Just like p squared equals lambda squared now. So this is ph squared goes like 1. This is pc squared goes like lambda squared. And now at lambda, this is where our anticollinear mode lives. Okay, so I didn't tell you what an anticollinear mode was, but it's pretty clear. You just point it in the other direction, right? And then up here, we have our collinear mode, Cn. And then down here is p soft squared, or ultra soft, goes like lambda to the 4th. And it lives here, right? So that's our ultra soft mode. So this is the hard mode, ultra soft. And this is lambda squared. Okay? So this is a beautiful, I think this is due to Ian, this is a beautiful way of representing the modes of the theory, right? We're going to have up here this hard scale, which in our power counting is parametrically separated from the collinear and the anticollinear scales, which are then parametrically separated from the ultra soft scale, right? And the power counting, the virtuality of these particles, right, how far it is from the mass shell, separates these out for us, so that these issues that, I forget who asked, somebody asked about double counting, are taken care of in the same way they were taken care of in the simpler example at the beginning of lecture, okay? That's to be contrast with SCET2, okay? So I'm starting to run out of time, so let me not be quite so careful with all the labeling. We have a hard scale, and then at lambda squared, we have Cn bar, we have Cn, but now we have C soft on the same parabola, right? Because its components all scale like lambda. So what do you do? Well, you have to worry about now separating these from each other. And the way that they're separated is in rapidity. So the collinear particle points this way. The anticollinear particle points that way. The soft particle is everywhere. So if you introduce an additional regulation in terms of rapidity, so then you'll carefully separate the soft modes from the collinear modes. Yeah?
If you have like a soft particle, then it has another loop. So then we don't have a very separable scale, right?
No, but the scales are determined by the process that you choose, right? So you're choosing a process where, so you're making these two particles at some high scale, call it big M squared, and then you want to measure, say, a cone around them of order little m squared, right? So that gives you a big separation of scale. So it's really in terms of your observable, not in terms of, right? I don't know if that gets to your question, but the scales when we talk about the scales, we're really talking about the physical scales in the problem, right? And then the loop momentum goes over all momentum, like we saw in that method of regions example. Okay. No, this is going to let us power count the loop the same way we did in the.
So just from this parameter.
Yeah. And the only thing, I'm not going to actually have time to tell you guys about this in detail. I just want to point out that there's this subtlety. And again, if you look in Ian's notes, he'll draw these pictures for different processes. And so just be wary that when you have to work with the soft modes and the collinear modes, then you have to separate in rapidity. Okay. So in the Becker notes, this comes up in the massive Sudakov integral, which I think I'll write down for you just to show you an example of an SCET2 process, but we won't have time to analyze it in detail. We're going to focus on the SCET1 example. It's hard enough. Okay. Good. Wow. All right. So.
What is the point of the integral? Because I feel like that's not a single. So like if you produce a particle that's going 180 degrees opposite you, there's no difficulty in distinguishing the two particles. They're going to be in very different places, not on top of each other.
So I'm going to show you tomorrow the Sudakov integral is going to have divergences associated with both directions. Okay. And it really is because what we're really modeling is back-to-back production. So you can have fluctuations on this side, or you can have fluctuations on this side that give you divergences. Okay. You can't just make a single hard line out of nothing. Right? Yeah. So I'm basically out of time. I apologize for not making this quite as connected to physics as I wanted. The next thing I was going to do was going to sketch out some diagrams, but I think that'll be a nice place to start next time. Maybe let me just tell you what we're going to do for our last lecture. And I'll only take about 30 seconds. So I was going to make a point about how the infrared structure of gauge theories work, or of just field theory generally. So I'll make that point at the beginning of next time. And then we're going to look at the following process in gory detail. So it's going to be our same Lagrangian, okay? We're going to have J make us, and this, by the way, is kind of misleading, right? This is really two back-to-back lines, okay? But connected by a loop of the little phi's. And this integral is a squared integral dl 1 over L squared times 1 over L plus P1 squared 1 over L plus P2 squared. Okay? This integral has soft and collinear divergences. So I'll show you that in detail next time. And then what we're going to spend probably most of the class doing, frankly, is expanding this in regions, okay, in terms of the SCET1 modes. And we're going to see how to do how this integral beautifully decomposes into these different sectors. And then I'll tell you a little bit about how we use that to then resum the large log squared that emerges in the infrared. Okay. So yeah, I think it'll be a lot of fun. We're going to build on this. Right, so hopefully you see this continuous thread, right? There's a reason that I showed you this heavy light integral in this toy theory, because now we're going to a slightly less trivial toy theory, where we're going to use all of the same techniques, and I'm not going to be able to have time to do everything in detail to the way that I did in the other case, but everything works exactly the same, right? All those principles were general. So we're just generalizing to a more complicated process. There are going to be some really cool, like very clever physics points along the way, about how we actually resum infrared divergences instead of UV divergences, so I'll make a point about that. And then I'll show you how to actually compute some of this in detail and how to resum the Sudakov integral, the Sudakov logs associated, right? There's two logs because you have a soft divergence and a collinear divergence. Yeah, so I think that's a nice place to stop for today. I'm happy to take more questions. We can talk over coffee, anything. All right, thanks.